Okay, hi everyone. My name is Juliet, and this is the proposal presentation for my master's research, Machine Learning of F18 Sodium Fluoride PET-CT Radiomics Features for Prediction of Coronary Calcification Scores. And my supervisors are Martin and Jake. So the keywords of my master's research are coronary artery calcification, sodium fluoride PET scans, radiomics, and machine learning. And the ultimate benefit that we seek are better risk stratification, early diagnosis, and prognosis for coronary artery disease. And in this presentation, we'll be going into these topics one by one. Before jumping into the presentation, here is a list of terminologies and acronyms that we'll be using in this presentation. I believe everyone's quite familiar with them. So again, these are the topic of this presentation, and we'll be going into these topics one by one. So without further ado, we'll go into the first topic. What is the aim of the project? So the principal aim of this project is to predict the follow-up coronary calcification score, which is about 2 to 3 years after the baseline, for the 4 coronary arteries using the radiomics features extracted from the baseline F18 sodium fluoride PET-CT scans. And again, these are the keywords for the research. The principal aim can be further broken down into 4 smaller goals. The first one is a continuation of a project conducted by a previous master's student, Keaton Wright. He developed an auto-segmentation model using NN-UNet for coronary artery and aorta segmentation. And we want to be able to compare the radiomics features extracted from the manual segmentation from the clinicians and the automatic segmentation from the NN-UNet to make sure they agree with each other. So that's a continuation of the previous project. Additional to that, we also would like to examine the individual radiomics features relevance to coronary calcification progression. We also would like to build regression models for the calcification score prediction using a combination of multiple radiomics features to find the best model. If time permits, we also would like to evaluate the application of such model to the clinical workflow. So why coronary artery calcification? Why is it important? We'll go into the next section and explain a bit more. So this is the graph from WHO, and as can be seen, ischemic heart disease, which is another name for coronary artery disease, has continuously been the leading cause of mortality in the world since the beginning of the 21st century. And the number of deaths is growing over time. And according to WHO, cardiovascular disease in general are responsible for about 17.9 million fatalities annually, contributing to 31% of the global mortality. And coronary artery disease alone is responsible for 9 million deaths annually, making it the highest cause of mortality among all causes in the world. And there's an increasing prevalence that's been observed by the American Heart Association. It is predicted that this number could escalate to more than 23.6 million by the year of 2030. And that's why it is important, something that we want to investigate and reduce. What's the origin of coronary artery disease? So it is a subset of the general category of cardiovascular disease and is caused by accumulation of atherosclerotic plaque within the coronary arteries, which will narrow the artery and restrict the blood flow and oxygen delivery to the heart muscle that does not allow the heart to function properly. And what are the symptoms? So such plaque buildup can lead to symptoms like chest pain, short of breath, more severe symptoms like heart failure and heart attacks. And most of the times, the coronary artery diseases can progress quite far before any symptoms is observed. This silent progression makes it important for early detection and risk stratification. So here is a picture taken by research by these two people. It's a picture of a severe coronary calcification patient in the end stage. So since because of the silent growth, how can we predict it? Is there any predictors that we can use? In 1990s, this guy called Agaston came up with a way to quantify the coronary artery calcification using CT scans. So he uses these threshold value, 130 HU and 1 millimeter squares, for each one of the calcific lesions and adds them all up as the total score for coronary calcification score. And such quantification method has been proven to be highly correlated with the incidence of cardiovascular events by literature. And it is currently being used in clinic as one of the important risk factors by clinicians. So for now on, when we talk about coronary calcification, we are referring to the Gaston score. Now, but the score itself is not enough for us to get a full picture of what's happening in the heart. We need more information. So in the next section, we'll go into the topic of cardiac imaging and especially the potentials of the sodium fluoride PET scans. These are the major modalities of cardiac imaging. Each one of them are used in different use cases. For example, cardiac CT scans are typically used for calcification score calculations. Angiography is good for coronary artery stenosis detection. Cardiac PET scans and the cardiac dissuspect, they have similar use cases, and the PET scans are starting to replace the SPECT scans in clinic. They're both used to detect myocardial perfusion and metabolic activities in the heart. There's also the cardiac MRI, which is good for cardiac function assessment and tissue characterization. And this study will be focusing on the cardiac PET scans. And as mentioned before, the calcification scoring, although it's a useful risk factor, it has lots of limitations. For example, because the threshold is used, it's overlooking those microcalcifications that can be missed. Also, there's no information on the temporal dynamics of the lesion. It means that we don't know if the lesion is currently active and progressing or if it's stable. We only know what it is right now. So we need something else, something better. So originally used as a bone tracer, sodium fluoride has demonstrated great potential in cardiac imaging. It is said that it can detect increased signals for microcalcification, that's less than 50 micrometer in early stage of calcium development. That is often missed by traditional CT scans. There are also many research showing the potential of sodium fluoride as a reliable predictor of a coronary calcification progression. It means higher uptake of sodium fluoride locations usually correlates to like a high progression of the calcification in that location. And in this study, we'll try to quantitatively predict the follow-up calcification score so that the clinicians can use it as an additional risk factor to perform better risk stratification and patient management. So this is a study that's conducted here locally at Charlie's by one of the cardiologists to detect the potential of sodium fluoride F18 in calcification progression. So the first column is the baseline CT scan, and second column is the baseline PET scan, and the last column is the follow-up PET scan. So for the two rows are the two patients. As can be seen, at the baseline CT, the two lesions have similar calcification level, but at the baseline PET, one lesion had much higher uptake than the other, and the follow-up calcification about 2 to 3 years down the road, the lesion with higher uptake has much higher progression comparing with the other one. So most of the studies on sodium fluoride PET scans are only exploring the uptake value of sodium fluoride. I was not able to really find any literature that used complex radiomics features on sodium fluoride PET scans. So our study aimed to explore this gap in current literature. So we want to use radiomics on sodium fluoride PET scans to use the full potential of it. So we're going to the next topic, radiomics. The Image Biomarker Standardization Initiative standardized the following radiomics features. Firstly, the first order radiomics features, including intensity, etc. There's also the shape and size that describe the geometric characteristics of the caddic structure. And the rest of the 5 are the high-level texture features, including gray level co-occurrence matrix, gray level round length matrix, gray level size zone matrix, neighborhood gray tone difference matrix, and gray level dependence matrix. I will not go into the details of what exactly each one of the radiomics features category, what it means and what it does, but in general, they're quantitative, high throughput information from medical images that allows for statistical analysis. So Python, our good friend, has something that's already ready for us. So the PyRadiomics library has been developed for radiomics feature extraction that closely follows the guidelines of the IBSI. So before the radiomics feature extraction, image processing needs to be performed. These includes image filtering and grayscale discretization. Discretization is needed for texture feature extraction. So image filters, there's a large range of image filters can be applied to the images that has the potential to enhance certain features or degrade certain features. So before the radiomics feature extraction, there's different filters that can be applied to individual image. And a combination of these filters and the images can lead to a very large feature space for our machine learning algorithm. Grayscale discretization needs to be specified for the texture features. So because of the gray levels are a continuous scale, we want to be able to do this, want to break it down into different levels for the texture feature extraction. There are two methods, fixed bin size and fixed bin number. I won't go into the details here, but fixed bin size is recommended for PET scans. And again, Python have this library that we can just call and define the parameters and extract all the radiomics features. Now we have our radiomics features extracted from the PET scans, so we can apply the machine learning algorithms to it for prediction of the calcification score. It was recommended by the clinicians that we use regression models to directly predict the follow-up calcification score. So we'll be using regression models in this study. And there are majorly these regression models that we can explore: linear regression, support vector regression, random forest, gradient boosting, principal component analysis. Each one of them have a fundamentally different mathematical algorithm behind it. We'll evaluate the performance of all of those models and find the best one. In addition to the models, feature selection is needed. As mentioned before, because of the high dimension of the feature space, we can easily overfit our training set. So dimensionality reduction is needed if we don't want to overfit the training set and have a better generalization capacity for our model. And also K-fold cross-validation and grid search will, as a typical machine learning techniques, will be used to find the best combination of hyperparameters for each one of the machine learning algorithm. And the performance of each one of machine learning algorithms will be compared with each other to find the best model. Now we're going into the project planning and the proposed timeline for this project. The data set that will be used for this study is the VICOVAC cohort conducted here at Charles, I believe, by cardiology department. There are 149 subjects with diabetes, aged between 50 to 80 years old. All of them have baseline CT and baseline PET. They're screened for the calcification score above 10. That's their screening criteria. And 41 of those patients have a follow-up PET and calcification scoring about 2 to 3 years after their baseline. Out of all of those patients, 141 had manual segmentation for each one of the coronary arteries by the clinicians, and 28 of the patients had the UNET segmentation by the previous master's student. So out of those regions of interest, out of all of those patients, we'll be performing image filtering, gray cell discretization, and then extract radiomics features using the configurations. After the extraction, we'll be performing feature selection. So there are machine learning algorithms that can train the model while reducing the dimensionality of the feature space at the same time. But in literature, usually this methodology is used. It's got maximum relevance and minimum redundancy, which means highly correlated features will be removed to only leave one of them in the feature space, and only the one with the highest correlation to our target will be left in the feature space. And the model training will use multifold cross-validation and grid search, and the performance of each model will be evaluated against each other. To note here that I also have a step called further exploration. This is if time permits. There are also things that we might not have the chance to do in this study, but we can do it, and it will be good for the study. First is model interpretability. Is a lot of times the black box models doesn't give good transparency for the clinicians to understand what exactly is happening in the background, so they don't trust the machine learning model and their predictions. So there's this article published online about explainable AI to help to explain machine learning models to people who doesn't understand machine learning. This will be a good thing to do. Second thing is take into consideration the clinical factors. So far we're training the model purely on the radiomics features, but we know the clinical factors can be used, and there'll be good features to help with the prediction. There's longitudinal analysis. That's to analyze the follow-up PET scan to kind of further predict the calcification in the future, see what we can learn from that. We can also deploy deep learning model regression models. We didn't include that in our study is because deep learning models kind of does not use radiomics features, and the features are kind of more abstract for people to understand. So we left it in the further exploration part. There are also many challenges for this study that we could encounter, and we need to take into consideration when we are doing this study. The first one is the resolution and noise of PET. Because of these kind of native limitations of PET, it could highly affect the quality of the radiomics features. The second one is the repeatability of radiomics features. There are indicators that suggest that reconstruction settings, segmentation algorithms, and these things can significantly impact the value of the radiomics features more than the lesions themselves. And these are the things we need to take into consideration. Also, clinical factors, our patient comorbidities and their demographics. These are the factors that we're not taking into consideration when we're doing a calcification prediction. And another one is data quality and quantity. We don't have a large, we have a relatively okay volume of data set, but it's not large enough. So we have to think about what are the things we can do so the model does not overfit the training set. The model generalization capacity. It's here to note that this model is trained on diabetic patients of certain age range, which means the model might not be applicable to the wider population. Last is model interpretability. Again, as mentioned before, lots of the machine learning models are black box. It lacks transparency. So we have to think about this to kind of explain everything to the clinicians on what exactly is being happened in the model and why certain calcification score is being predicted. So this is the timeline of this project. So thanks to the previous master's student, Keaton, the data are already nicely formatted in nifty format, and I've already performed initial feature extraction on the original scans without any image filters and default grayscale discretization. And I've already did some initial comparison between the manual and auto segmentation. And we're in the middle of extracting the features again using combinations of filters and different grayscale levels. And further on, we'll be doing the model development in June and writing our thesis and all of the other stuff. So in conclusion, that is the keys to this project. That's the core of the project, our keywords and our ultimate goal. Thanks, everyone.
Okay, thanks very much, Juliet. Brilliant presentation. Very professional. Thanks.
Thank you. Thanks, Fetchman.
No worries. Questions from Juliet, although it's very clear what questions. Yes,
Well
go
done,
ahead.
Juliet. Mubasha, do you want to jump in first?
Yes.
Yeah, fine, Jake, you go ahead, please, first. That's fine.
Okay. Yeah, well done, Juliet. Just wanted to say a really good presentation. It was very clear. I do have a couple of questions. So first of all, you mentioned the Agatston score. Is that what you're trying to predict in this data set? Is that your ground truth?
Yes, that is our ground truth.
Okay.
So, yeah.
Cool. So that's the ground truth. You also mentioned that your total data set size with follow-up imaging was only 41, I believe.
Yes.
Do you have access to ground truth data for the remainder of the patients? Was it approximately 150 or so? Like a Agatston score is what I mean.
There are only 41 patients that kind of respond to the follow-up. So basically, after 2 years, I believe the clinicians send out like a questionnaire asking who want to come back and do another PET scan, do another CT scan, and only 41 has responded. And that is why the follow-up is like from 2 to 3 years, depends on, when they come back. Yeah, So
I guess the size of the data set that you have access to actual ground truth data for is 41 then, right? So you'd only have access to the Agatston score for those 41.
Yeah.
Yeah.
But there's one thing is because the 41 patients have region of interest at per coronary artery level, so our actual data set, the size is 41 times 4. Since we can break it down into per coronary artery, so to increase the size of our data set. So
right.
Kind of
so there's are you saying there's an individual score for each of those arteries?
Yeah, exactly.
Okay. Right. I did have a few other questions. So what clinical data do you actually have access to? Because it seems to me that there are some important clinical parameters that you could include in your model building. And there's actually a lot of evidence just in the radiomics field in general that including sort of known prognostic clinical factors into your model building process improves the performance of your model. What clinical factors do you have access to, or do you think would be important, I guess, to include?
So yes, I think I read the same study. The clinical factor is actually quite important. So we've had interviews with the clinicians, and he mentioned there is a very large range of clinical data if we want, but he will kind of need to explain. So right now we have some very basic data like age, I think, like heritage, what type of, I think there's also height, this type of very basic data. But I believe the clinicians mentioned they'd also have all of their blood tests and all of the medications that they're on, the blood pressures and et cetera, IBM. And yeah, basically there is a very large range of clinical data that we can use and explore if we want to. We just need to kind of have another chat with the clinicians and see what they recommend.
Yeah. Okay.
Yeah.
Cool. I had one last question. You mentioned that repeatability was important. Have you identified any repeatability studies in this area that you could use to sort of see what sort of changes in SUV parameters will be required?
Yes, I have identified. Sorry, I got it. I'm getting a little bit feedback from. Okay, it's gone now. I identify Nathaniel's PhD thesis was quite a good source to reference repeatability. So I believe he mentioned there are a couple filters that is good to improve the repeatability of certain features. I don't really remember which filters, but I think we can try similar filters in our image to see if the model actually recognizes those features to be more relevant.
Yeah.
Yeah.
One thing I would just suggest is that repeatability is going to be dependent on the tracer that's used.
Yeah.
So for example, in my repeatability analysis, some of my conclusions different from Nathaniel's. So I think I'd be careful generalizing the repeatability stuff to traces other than what you're using. Okay.
Cool.
Yeah, so maybe if there's any sodium fluoride repeatability stuff, that'd be a good place to start.
Oh, thanks very much, Jake. Can I have your repeatability paper just to have a look?
Yeah, I can send it through to you. Yeah.
Thank you very much.
Sorry, I'll leave it open for others to ask questions now. Sorry.
Thanks very much, Mubashir.
Hi, good presentation, Juliet. I have a couple of questions. First of all, my background is not from medical, so please, for my apologies. When you are saying this calcification scores, what is the range of calcification score?
The region or?
No, like you have said that you are trying to predict, the machine learning algorithms will try to predict the calcification score. So what is the range of calcification score?
The range, sorry,
Range.
It is, I'm so sorry. The internet here cut off in halfway. So the range is around from 0 to all the way up to thousands. And usually there's a lot of articles online that's arbitrarily saying above or below 400 should be used as a landmark. Yeah, but these are all quite arbitrary.
So how do you plan? Like, it's very difficult because you have a very small data sets. How can you compare it with the machine learning algorithms of the output? Because if it is such a high range and you have 41 times 4 or even 150 times 4, whatever the results, like less than thousands of the values, how you will compare with the output of the machine learning, and also how you will be training with such a small data set because it has no diversity actually. So are you grouping them up? What's the plan for that?
So I think comparing with a lot of the other radiomic studies on PET, this data set is like still kind of okay. There's a lot of other studies with even smaller. We still need to kind of split it into training and testing. We have 41 times 4, which is about 160. So we still have to split it into training and testing to evaluate. And because initially we have 149 patients, there's a potential that we can do some semi-supervised training, even though it's very hard to validate the performance of semi-supervised training models. This is a space that I kind of need to do more investigation to see what are the best methods to use.
Okay, just a couple of suggestions regarding your research I would like to make. First thing is that if you have a score range of 0 to 1000, so you need to have the samples for each and every value. Otherwise, machine learning algorithm cannot be actually properly trained. Unless and until you group them in hundreds or 250s range or something like that. And then you say, okay, this is group 1, this is group 2, this is group 3, and this is group 4. And that you can get some help from the clinicians so that they can guide you how to group them. This is the first. Otherwise, machine learning algorithm cannot do anything, or any results from the machine learning algorithms will not be reliable. Because if the range is 1000, you need to have at least more than 1000 actually samples to train it. For each and every value, you should have 1 or 2, at least 2 cases. Otherwise, you cannot predict the scores properly. Second thing is that in your case, the score is basically something which cannot be considered as class. For instance, if you say the score is 10 and your model predicts it as 20, so 10 is far from the 20. But if it compares it and grades it or predict it as 11, it is closer. So now you cannot actually divide them into the classes. So you have to look into it that maybe you are looking into the Spearman correlation component or something like that, so
Yeah.
that actually you can figure it out how you are going to compare the results. Okay, so machine learning part is basically where you need to investigate more and try to understand that how you can actually categorize this problem. Because with such a high range of scores, it is not possible to use machine learning with such a small data set.
Thanks, Mubasha. Is your recommendations to more towards classification, to do, if it's possible, to go more towards the classification approach, even though we
Yes.
can have to make the, okay, cool.
Yeah.
We'll have another chat with the clinicians again.
Okay, thanks. Well done.
Okay, great suggestions. Thanks, Mubasha. Any other questions? All good? Happy? Excellent. Thanks very much, everyone. If you could please, Martin, turn off the record.